Now I will quickly take you through the double integration method, which is one of the three methods that we discussed in CE 343 to evaluate slopes and deflections. The double integration method is based on four important assumptions. The first important assumption is members are initially straight. That means double integration method cannot be used for curved beams. The loads should be perpendicularly applied, and you cannot use this method to evaluate the slopes and deflections in beams on which inclined loads are applied. When double integration method is used, the length of the beam should be much higher than the width and depth of the beam. The slopes and deflections in the beams should be very small when the double integration method is used. These are the two equations that we use for evaluating the slope and deflection respectively. Here I denote theta as slope. Slope is nothing but the angle made by the tangent at a particular point with respect to the x-axis, where the tangent is drawn on the beam at the target point. Here V is the vertical deflection of the beam. So theta, the slope of the beam, is nothing but the derivative of the deflection with respect to x and is given as the integral of m by EI, where m is nothing but the bending moment equation and the EI is a constant, which is flexural rigidity. E is Young's modulus and I is moment of area of the section of the beam. So the deflection is obtained by integrating m by EI twice, and this m by EI and this m by EI are exactly the same. Let's look at the sign convention now. If for some reason the slope value turns out to be positive, that means the slope should be counterclockwise measured from the x-axis. If the deflection turns out to be positive, that means the beam should deflect upwards when compared to the undeflected beam. So when you do this integration, in the case of single integration which we do to evaluate the slope, you get one constant per integration. When you integrate this equation twice, you get two integration constants. The constants of integration can be evaluated by using boundary conditions and compatibility conditions. I'll make these two things clear when we solve a simple example. Here I'll quickly take you through one simple example that demonstrates the use of double integration method to evaluate the slopes and deflections at every point in a given beam ABCD. Here we have a uniformly distributed load of 3 kN per meter in the span AB, which is 12 meters long. There is a concentrated load on the beam at the point C, which is 24 meters away from the point A. In order to evaluate the bending moment equations, we have to divide this whole beam into three spans, because these are the three spans in which the loads are not changing. I'm not explaining how I evaluated these bending moment equations because I have discussed this concept at length previously in this course. So now to evaluate the slope of the span AB, we need to use the first equation, which is nothing but theta is equal to dV by dx is equal to integral of m by EI dx. For this particular example, I chose an EI value of 1. I already know the equation of m here. I substituted the bending moment equation for the span AB here and then divided it by EI and then integrated it using dxi. After the integration, I am left with this equation, and this equation has an integration constant C1. In order to evaluate the deflection equation for the span AB, I take this equation and then integrate it once again, but this time I'm not dividing it with EI because I know that the value of EI is 1. When I integrate this equation, I have this complete equation, and in this equation I have two constants, two integration constants C1 and C2. I have to repeat the same procedure for the span BC and the span CD. How did I do that? I just integrated the m by ei equation once in order to get the slope, and when I integrated the m by ei equation once, I get one integration constant, and when I integrate the m by ei equation twice, I get two integration constants in the deflection equation. So when I did the exercise, once again for the span CD, I have once again two more integration constants. So now I have 6 integration constants. They are C1, C2, D1, D2, F1, F2. In order to know the slopes and deflections of the spans AB, BC and CD, I have to evaluate these 6 constants. I can evaluate these 6 constants by making use of the boundary conditions and also some slope and deflection compatibility equations. As I previously mentioned, we can evaluate these 6 constants of integration by means of boundary conditions and compatibility conditions. Boundary conditions are those that you see at the supports. For instance, at the support A, the deflection should be equal to 0. At the support D, the deflection should be equal to 0. Please remember that this is a pin support and this is a roller support. Both of them allow rotation of the beam at the points A and D, and rotations at the point A and D are not equal to 0. That means the slope of the beam at the point A and the slope of the beam at the point D are not equal to 0, and they cannot be considered to evaluate these constants. We just have two boundary conditions. Once again, what are they? Deflection at A is equal to 0 and deflection at the point D equal to 0 because of the pin support and the roller support here. We need 4 more equations to find out the other 4 unknown integration constants. We make use of the compatibility conditions. What do I mean by compatibility conditions? The compatibility conditions are given here for this particular beam. Say for example, at the point B, the slope that you measure in the span AB should be equal to the slope that is measured in the span BC. That means essentially there is no slope discontinuity. So the slope in the span AB is equal to the slope in the span BC. So if you evaluate the slope in the span AB by substituting x1 is equal to 12, that should be equal to the slope in the span BC where x2 is equal to 12. Similarly, the deflection in the span AB at the point B should be equal to the deflection in the span BC at the point B. By using the same logic, we can find out the slope at the point C in the span BC and equate it to the slope in the span CD at the point C. The point C is where x2 is equal to 24 and x3 is equal to 24. We will have one more compatibility equation when we equate the deflection at the point C in the span BC with the deflection at the point C in the span CD. So in total, we have 2 boundary conditions and 4 compatibility conditions. In total, we have 6 equations which we can use to find out these 6 unknown constants. You have to simultaneously solve these equations to get these 6 unknown constants.